So today we're going to be talking about strength of acids. And of course, what we always do is we put numbers to it. The values that we're going to use to determine the strength of acids are represented by Ka. And hopefully when you see the K, it makes you think of an equilibrium constant. Ka, the A in the Ka stands for acids. And to do that, we're always going to start to figure it out by writing an equation. So even though it's going to get into mathematical problems, I always want you to start any Ka problem by writing out an equation. Now, I couldn't on this PowerPoint do different size arrows, but when I come back, I will show you how we can use arrows to represent that as well. And Ka is an ionization constant. So what last semester we called dissociation, now with acids we're going to call it ionization. So let's take, for example, acetic acid, which is what you have in the equation here. Once it gets put into water, it immediately ionizes. Now you can write the equation with the water or without, it doesn't matter, but water is not a part of the equilibrium expression. Okay, it's only the products over reactants minus the water. So you see the equation there for the ionization of acetic acid. So in general, it's a hydrogen ion times the concentration of the anion over the initial concentration of the acid. And so if you think about that equation, it's products over reactants. So if you have a lot of dissociation, then Ka is going to be very large. If barely any of it dissociates, it's going to be very small. So what you see here is a list of acid strengths. You notice that I didn't say that there was any medium strength acids, and that's the case. Either the hydrogen is more attracted to the anion or those ions are more attracted to the water. And also, if you have a strong acid, if it all ionizes, the denominator will be 0, and you know we don't do that. And so that's why I'm just saying here that Ka is very large. So this is just a table to give you some idea of what the Kas look like. How are you going to know if something is a strong or weak acid? Well, you actually have to recognize these numbers and memorize these numbers if you're not given the Ka. So put these acids in your notes. Again, these are the acids that you have to memorize that are strong. And if I ask you if something is a strong or weak acid, for example, if I say, is acetic acid strong or weak? You'll say weak. And if I ask you why, you'll say it's because it's not strong. It wasn't on the list. There's only one acid or one base that I'd like for you to memorize, and that's ammonia or ammonium hydroxide. That's our weak base that we'll be using in this unit. Every other base that has hydroxide at the end is going to be a strong base. The other thing that we're going to calculate today is percent ionization, which is, notice there's no anion in this equation. So it's just the concentration of the hydrogen ions over the concentration of the acid. A is not a real thing. That's just some hypothetical anion that's written there. Okay, so let's start to do this. The question is, calculate the Ka for a 0.1 molar solution if the HF if the hydrogen ion concentration is 8.13 times 10 to the negative third molar. So let me show you the answer for this. Again, as I mentioned earlier, whenever you're doing a Ka calculation, no matter how simple and no matter how many times you've done it before, I still want you to write out the equation. So here's my solution. I wrote out the equation, and then underneath, I wrote the concentrations that were given in the problem. Do you notice the initial concentration was 0.1 of the acid? The concentrations of the H plus is 1.3 times 10 to the negative third, but you notice H plus and F minus are in a 1-to-1 ratio, so that's why I squared the numerator. And then we just plug it in to the equilibrium expression for Ka. Now we can calculate something a little bit different. This question says, what is the concentration of, you don't have to know what this acid is called, it's benzoic acid, but of the anion if the concentration of the acid is 0.0718. And what I neglected to say on the last question is, when you're starting the problem and when you're writing out the equation, before you do even one number of the math part of it, you have to decide if it's a strong or a weak acid. And the reason for that is, if it's a weak acid, you'll do it like the previous problem. But if it's a strong acid, we don't use a Ka calculation because if you remember that table, we just say it's very large. Because what does it mean to be strong? To be strong means it all ionizes, which means the denominator would be 0. So write the equation and then again say to yourself, okay, is this a strong acid or a weak acid? If it's a weak acid, I'm going to do Ka. If it's a strong acid, we're going to do things differently, and I'll show you one like that. So it says, what is the concentration of the anion? And then we're going to ultimately figure out the pH. So once again, we're going to start with the equation. We have the acid, and that breaks apart into the anion and hydrogen ions. So in this case, because again, it's a 1-to-1 ratio, which by the way, for these weak acids, it's always going to be a 1-to-1 ratio. So in the numerator, we'd have X for the C6H5COO minus and X for H plus. So that's X squared in the numerator over the initial concentration of the acid. And then we just solve for X. Now remember, what are we letting X represent? X is the concentration of the hydrogen ions. So once we solve for X, we just take the negative log of it, and that gives us the pH. Now, this one is the first example that you're going to see that deals with a strong acid. How do we know that it's strong? Well, we know that it's strong because we have it memorized on our list. Now, remember, a strong acid will have 100% dissociation. What that means is there will be no HCl left once ionization has occurred. So when I write out this equation, HCl yields H plus and Cl minus. The concentration of the HCl that I made was 0.884. However, once it ionizes, there are no molecules of HCl left. It all becomes zero. So what was 0.884 HCl is now 0.884 H plus and 0.884 Cl minus. Well, if I know the concentration of the H plus, I can just take the negative log of it, and that will give me the pH. Okay, so let's do another one. We see here that we have the same concentration, but this time it's of a weak acid. Two ways to know that. Number one, it's not on your list of strong, so you know it's weak. And the second way you know it's a weak acid is because I'm giving you a Ka. We don't talk about Kas for strong acids. So once again, we're going to start by writing the equation. The concentration of the acid is 0.884 like it was in the previous problem. The concentration of H plus is X, and the concentration of the anion is also X. So it's X squared over the initial concentration of the acid is equal to Ka. Solve for X. X represents the hydrogen ion concentration, so I just take the negative log of it, and that will give me the pH. One more, you can see here, same kind of a question, so I'm going to just not bother to explain it. You can just take a look at the solution, but it's X squared over the initial concentration of the acid. That gives us the hydrogen ion concentration, and then we take the negative log of it to get the pH. Our next problem is a problem where we're going to figure out the percent of ionization. Now, I want you to think about this logically for a minute. First of all, decide, is acetic acid strong or weak? Well, it's weak because it's not on your list of strongs. Also, we know it's weak because it's Ka. So what would be your guess as to the percent of ionization? By definition of it being weak, we know that acetic acid should have a very low percent ionization. Okay, and let's see if that's the case. So we're going to start again by writing out the equation. We're going to do how we did it before and solve for X, which X then represents the hydrogen ion concentration. To get the percent of ionization, we take the hydrogen ion concentration. Please notice here that the numerator is not squared when you're doing the percent, over the initial concentration of the acid times 100. And as predicted, we get a very low percent ionization, less than 1%, which again, that's what we would expect if we have a weak acid. Okay, here's a similar problem, but we're just doing things a little bit differently. Okay, again, this is not a real acid, it's just some generic acid. So we're going to start by writing the equation. We know that it's weak because I'm asking you to solve for Ka. So if the percent of ionization is 2%, that means that the hydrogen ion concentration, which we don't know, we'll call that X, over the initial concentration of the acid, which is 1, is equal to 0.02, which is the decimal equivalent of 2%. We solve for X. X gives us 0.02. What does X represent? X is the hydrogen ion concentration, which is also the same as the H minus concentration. And so we just square that, put it over 1, and solve equal to Ka, and that will give us our Ka. All right, I think we're going to go ahead and skip this one because I only have 16 seconds left. Don't worry, do your best on this, and if you have any questions, we'll do it when we come back. Have a good day.